So what we have here is all of our amino acids kind of displayed and their originating molecules, or the molecules from which they could be synthesized. Now, one thing to keep straight is that these are not all uh, pathways in humans or anything like that, because there are essential amino acids that must come from your diet. Um, so this shows all of your different amino acids, or all the proteinogenic amino acids, and where they're coming from. So as a little bit of an example, what I want to show you guys is I want to show you serine coming from 3-phosphoglycerate, one of our metabolites in glycolysis. And then I also want to show y'all the pathway from which um, leucine, valine, and isoleucine are coming from pyruvate. Now, first and foremost, 3-phosphoglycerate. This serves as our precursor molecule for the synthesis of serine. Now, the steps involved in this process, first of all, we have a dehydrogenase reaction. So what we're going to be doing there is removing this hydrogen and this hydrogen in order to have our double bonded, our carbonyl oxygen. That will give us 3-phosphohydroxypyruvate. Now, the next thing that we need to do is we need to aminate this. Not animate it, aminate it. So we're going to use a transaminase. That will be phosphoserine transaminase. We've been talking about transaminases in the context of degradation, where we're moving a nitrogen away from an amino acid because we're trying to break down that amino acid. Well, in this case, since we're synthesizing it, we need to transfer an amino group onto it. So phosphoserine transaminase, you're going to use PLP, just like we previously did, glutamate, as well as that 3-phosphohydroxypyruvate are your inputs, and your outputs are 3-phosphoserine and alpha-ketoglutarate. Then what you need to do is, in order to get all that phosphoserine, you've got to remove that phosphate group. So you're going to make phosphoserine phosphatase. So that will help you remove this phosphate group. You're ending with that serine there. Now, the next step is to get to cysteine. Well, cysteine and serine are very similar to one another. The only difference is this hydroxide group versus a sulfhydryl group. Okay, so in order to do that, your sulfur donor is going to be your coenzyme A. So you're going to bring in acetyl-CoA and use that to produce serine acyltransferase. So you're going to transfer that on, that acetyl group, and when you have that, you're going to have to be using coenzyme A, so we've got acetyl-CoA, coenzyme A is going to be released. Then what we're going to do with our O-acetylserine is we're going to use O-acetylserine sulfhydrolase, or PLP, as our carrier, and we're going to be able to add a sulfide plus a hydrogen to make our sulfhydryl group. And out of that, we're going to release this acetate molecule. Okay, now our last bit of synthesis is going to be valine and leucine, and then finally isoleucine. I say valine and leucine together because they're kind of related. So our input is pyruvate. In addition to pyruvate, we're going to be bringing in a hydroxyethyl TPP. TPP is thiamine thiamine pyrophosphate. That thiamine pyrophosphate, that's going to be our carrier for what are ultimately this carbon and that methyl group, which become those guys right there, to make our alpha-acetolactate. That alpha-acetolactate undergoes a couple of reactions to give us alpha-ketoisovalerate. And then what we're doing, again, is an aminotransferase. Valine aminotransferase is going to take glutamate, our alpha-ketoisovalerate, and produce alpha-ketoglutarate, and lo and behold, valine. Okay, that alpha-ketoisovalerate is also going to be metabolized by a couple different reactions to give us alpha-ketoisocaproate. Okay, So our input there is that alpha ketoisocaparate glutamate, and our enzyme is leucine aminotransferase. We're going to have an output of alpha ketoglutarate and leucine. Okay, so there's our valine and leucine. They're going to go down a similar pathway, but there's a little bit of a branch here at that alpha ketoisovalerate. Okay, now our other reaction, in order to produce isoleucine, we're bringing in this. We have a starting molecule, pyruvate, because that pyruvate is going to be paired with our thiamine pyrophosphate to make our hydroxyethyl TPP. That hydroxyethyl TPP is going to be paired with alpha ketobutyrate to produce alpha aceto-alpha hydroxybutyrate. From there, we'll produce alpha keto beta methylvalerate. So this is similar to what we've seen before in terms of that valerate molecule that we're going to use again with the valine aminotransferase. So we're making isoleucine rather than, so we're making isoleucine here. Glutamate and alpha keto beta methylvalerate are going to undergo a transamination reaction where we produce alpha ketoglutarate and isoleucine. Okay, so one of the things that I'd like you to take away from this is that we have pyruvate as our starting molecule in all three of these. We have a transamination reaction, and this transamination reaction is always going to include glutamate as an input and alpha ketoglutarate as an output. So you should sort of look at this as what's a relationship between these things. Well, glutamate and alpha ketoglutarate, they're basically the same molecule, but one of them has been deaminated. We transfer that amino group onto valine, onto leucine, and isoleucine. All right. Well, I hope this is helpful. There are many other metabolic pathways for synthesizing amino acids. It's not of absolute importance that you have these memorized or anything like that. I think that it's important to understand them, to be able to look at them and understand pieces of information, or to understand like the high points of it and everything like that. But I'm not going to ask you to commit these to memory or anything like that. All right. Well, thank you very much and have a good one.